Okay, so I will try to give an overview of microinstability, kinetic microinstabilities. For my concern, I only have ion temperature gradient, electron temperature gradient, trapped electron mode, microtarion mode. So from the linearized velocity equation, we could arrive this expression for the distribution function. We have an adiabatic term and a non-adiabatic term, which can be this is a gradient, the total gradient term drift. D stands for drift frequency, and K parallel over V parallel. This is a collisional term, and that is zero. First kind Bessel function, zeroth order K parallel rho S. That is the gyro radius, and phi the static portion, and the electrostatic magnetic portion. So in general, as far as I'm concerned, the ITG is mostly electron is mostly adiabatic. So the GS I artificially added to here, which is just a number, indicates a portion, how much portion will be contributing the how much portion will be contributing non-adiabatically. So you can think GS as how much portion is non-adiabatic. So for ITG is ion non-adiabatic, electron is adiabatic. The ETG is exact opposite. Electron is non-adiabatic and ion is adiabatic. And trapped electron, because the electron has a banana motion, then we will have partially adiabatic, non-adiabatic electron. For MTM, it will be mostly electron contributing. So as far as I know, those first three can be characterized by drift type mode. This is affine type mode. So to have an intuitive understanding why those portion is adiabatic or not adiabatic, we can see this term. We can see this. So actually, this can have absorbed this term. I think it will be easier to see this way. So if we have a K per rho S, and we plot G naught square, just plot J naught, we'll have something like this. For electron, I have something like this for ion. The reason being, the gyro radius of ion is much bigger than the electron, as we know it. So we can think, well, at K per, at a high K per is large. A K per is large, then only a K per is large only. See, this is ion. This is electron. So the ion is almost gone. So for high K per, the electron is non-adiabatic. which means it will be mostly ETG. On the other hand, if we have a smaller K-perp, smaller K-perp, the momentum, the inertia of electron will recover the momentum really fast, and the gyro averaging effect doesn't influence ions much when it's small K-perp. Then it's mostly ITG, and since there's always some portion, if there's considerable portion have banana motion, it's trapped. The electron is trapped, then it will have TEM as well, trapped electron mode. Those are the, and also here in the intermediate we will have MTM. MTM I cannot have too much comments with. I haven't got too much details into that. ETG is non-adiabatic MTM, so it should be the same routine as ETG. So it's the electron non-adiabatic, maybe right before ETG, because ETG will take over fast. So ITG, ETG, TM, you can think it as in a way the temperature gradient is driven it, and MTM is temperature gradient driven, but this is more like a drift type, so it's just effectively fighting against the second law of thermodynamic. It has confined into a higher gradient profile, then it will just try its best to neutralize the gradient it produced. It's confined, so it just try to getting out of it. Those three modes. MTM will be more magnetic, so it will generate the magnetic islands. Then it will shorten out that region of in a way shorten out that region of gradient, because the particle can move freely between the current sheet. The current sheet is basically the width of the magnetic island. The particle can move freely in between. If it keep growing, then that will influence or have negative impact on the H-mode development. So that's the basic concept of all those type of mode. In terms of getting dispersion relations, I can just put a side note here. If you want to have dispersion relations, most of the time you can derive these dispersion relations by doing a closure, but using quasi-neutrality. And can be done by just the zeroth moment of the distribution, or the current, specifically naming an MTM. You can just calculate the first moment. First moment of the integral, and you can arrive to a dispersion relations. Then you can study the feature of all those different type of mode, which I will talk in a separate video in details.